this episode, we're going to make vectors and matrices feel like practical objects you can picture and reason with, not intimidating math symbols that only exist in textbooks. A lot of data AI work, including how models learn and how they compare things, depends on treating data as points and directions in a space, even when that space has hundreds or thousands of dimensions. When you can think in that geometric way, concepts like similarity, closeness, and change stop being vague words and start becoming measurable ideas. Dot products, norms, and distance metrics are the basic tools that let you measure those ideas, which is why they appear so often in machine learning and artificial intelligence, AI, thinking. The exam will not reward you for memorizing abstract formulas if you cannot interpret what they mean. So our focus will be on meaning, intuition, and common mistakes beginners make when they first see these tools. By the end, you should be able to describe what a vector is, what a matrix is, and what these measurements tell you about data in a way that sounds like a confident explanation rather than a fragile recitation. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A vector is best understood as a structured list of numbers that describes one thing in a consistent way, such as a user session, an email message, or a device snapshot. Each number in that list corresponds to a feature, which might represent something like counts, frequencies, measurements, or transformed values that capture aspects of the item. The key idea is that the vector is not just a bag of numbers. It is a coordinate in a space where each feature is a dimension. Even if you cannot visualize a 300-dimensional space, you can still reason about it the way you reason about a map. Every item becomes a point, and differences between items become directions. Beginners sometimes think vectors only exist when you draw arrows, but the arrow picture is just a helpful metaphor for direction and magnitude. In data AI, you mostly use vectors as representations, meaning you use them to encode items so you can compare, cluster, or classify them. Once you accept that a vector is a consistent representation, you can start asking meaningful questions like whether two items are similar, how far apart they are, and which features contribute most to that difference. A matrix is what you get when you stack many vectors together in a structured grid, and it is the natural way to store a dataset when each row represents an item and each column represents a feature. Thinking this way matters because many operations in data science are really matrix operations applied to many items at once. A matrix is not just a spreadsheet. It is a container that makes it possible to compute comparisons and transformations efficiently and consistently. Beginners often treat matrices as advanced math, but the basic meaning is straightforward. A dataset is a matrix when it is organized, so the same feature appears in the same column for every item. That consistency is what allows you to compare items fairly, because you are comparing the same kind of measurement in the same position. Matrices also help you see that features can be treated as vectors too, because each column is a vector of values across items. This perspective is helpful because it clarifies that you can reason both across items and across features, and many model behaviors depend on both views. Before you measure similarity or distance, you need a stable sense of what it means to combine or compare vectors, and that begins with understanding that vector operations respect feature positions. When you add two vectors, you add their corresponding components, and when you subtract corresponding components, which means you are comparing like with like. This sounds obvious, but a classic beginner mistake is to forget that the meaning of each position matters, and to treat vectors as if they were just collections of numbers you can shuffle without consequence. The whole point of vector representation is that position has meaning, because position is tied to a particular feature definition. This is also why feature scaling and consistent pre-processing matter, because if one feature is measured in very large units and another in tiny units, the large unit feature can dominate comparisons in a way that hides the contribution of other features. Even without doing any implementation, you should recognize the principle that a vector comparison assumes components are commensurate enough to be compared. If a question hints that one feature has a much larger scale than others, it is hinting that your distance or similarity calculations may be dominated by that feature, which can distort your conclusions. The dot product is one of the most important operations for building intuition because it connects directly to the idea of alignment. When you take the dot product of two vectors, you are combining corresponding components and summing them, which produces a single number that reflects how much the vectors point in the same direction in the feature space. If two vectors have large values in the same positions, the dot product tends to be large, suggesting strong alignment. If one vector has large values where the other has small or opposite sign values, the dot product becomes smaller, suggesting less alignment or even opposition. Beginners sometimes think the dot product is only a computational trick, but it is a geometric measurement with a clear story. It measures how much one vector projects onto another. This idea becomes important in many model types, because a model can treat an input vector as being scored by how aligned it is with a learned weight vector. When you see dot products in model explanations, you should think scoring by alignment rather than mysterious arithmetic. That mental translation is what makes the concept useful under exam conditions. It is also worth noting that dot products are sensitive to both direction and magnitude, which can confuse beginners if they do not separate those ideas. Two vectors can point in the same direction but have different sizes, and the dot product will reflect the sizes as well as the alignment. That means a very large vector can have a large dot product with many other vectors simply because it has large components, even if the patterns are not especially similar in a shape sense. This is one reason people sometimes move from raw dot product thinking to normalized similarity measures, because they want to compare patterns without letting sheer magnitude dominate. Another subtle point is that dot products can be influenced by negative values, which can represent directions that oppose each other in certain features. If your features are centered around zero or include positive and negative deviations, a dot product can capture whether deviations move together or in opposite ways. Beginners often feel uneasy about negative values in vectors, but negative numbers can be meaningful, like below-average deviations or direction of change. The main exam-ready habit is to ask whether you are comparing raw magnitude alignment or pattern alignment, because the dot product mixes both unless you normalize. Norms are the tools that give you a formal definition of vector length, which is a crucial idea because length influences how comparisons behave. A norm takes a vector and returns a non-negative number that describes its magnitude, meaning how big it is in the space. The most common norm people encounter is the Euclidean norm, which corresponds to the straight-line distance from the origin to the point represented by the vector. If you imagine the vector as an arrow from the origin, the norm is the arrow's length. This matters because many algorithms and interpretations assume that vectors of very different lengths represent items of very different intensity or scale, which may or may not be meaningful, depending on what the features represent. Beginners sometimes treat norm as another word for average, but it is not an average. It is a summary of overall magnitude. If a feature vector has many large components, the norm is large, and that can affect dot products and distances. Understanding norms helps you reason about normalization, which is the idea of adjusting vectors so comparisons focus on patterns rather than raw size. Even at a high level, recognizing when magnitude should or should not matter is a key judgment skill. Distance metrics are how you make the concept of closeness precise, and they matter because many data AI methods depend on the idea that similar items are near each other in feature space. A distance metric takes two vectors and returns a non-negative number that represents how far apart they are. The most familiar one is Euclidean distance, which corresponds to straight-line distance, the same idea you would use on a map. If two vectors are close in Euclidean distance, their components are similar in a squared error sense, meaning big component differences are penalized strongly. Another common distance is Manhattan distance, which sums absolute component differences and can be visualized as moving along a grid, like navigating city blocks. Beginners sometimes think there is one true distance, but distance is a design choice, and different metrics emphasize different kinds of differences. Euclidean distance tends to react strongly to large component differences, while Manhattan distance treats differences more evenly because it grows linearly with component differences. On the exam, if a scenario hints at outliers or heavy-tailed features, it may be nudging you to recognize that a squared distance style can be overly sensitive to extremes, while an absolute difference style can be more robust. The key takeaway is that distance is a formal definition of dissimilarity, and you must match that definition to what you care about. The relationship between distance and norms becomes clearer when you realize that Euclidean distance between two vectors is the norm of their difference. You subtract one vector from the other to get a difference vector, and the length of that difference vector is the distance. This is useful because it connects comparison to a simple geometric picture. The difference vector points from one item to the other, and its length tells you how far you had to travel in feature space. This also reveals why scaling matters so much, because if one feature has huge numeric range, differences in that feature dominate the difference vector, and therefore dominate the distance. Beginners often feel surprised when one feature controls distance-based behavior, but that outcome is not a bug in distance. It is a consequence of how you define the space. If you measure height in inches and weight in pounds and treat them as equally comparable without scaling, you have implicitly said 1 inch and 1 pound are equivalent units of change, which is rarely what you truly mean. This is why normalization or standardization is often used conceptually, because it makes features comparable so the geometry reflects meaningful variation. The exam might not ask you to perform scaling, but it will often test whether you understand that comparisons depend on the coordinate system you chose. Cosine similarity is a concept closely tied to dot products and norms, and it helps you separate direction from magnitude in a way that is intuitive once you see the purpose. Cosine similarity measures the angle between vectors by using the dot product divided by the product of the vector's norms. The result reflects how aligned the vectors are regardless of their lengths, meaning it focuses on pattern similarity rather than raw size. This is useful when the overall magnitude is not what you care about, such as when two documents have different lengths but similar topic composition, or when two user sessions have different total activity but similar relative behavior. A beginner misunderstanding is thinking cosine similarity is automatically better than Euclidean distance, but it depends on what the data represents. If magnitude carries meaning, such as total volume or intensity, then ignoring it may throw away useful signal. If magnitude mostly reflects irrelevant scale differences, then focusing on direction can be more meaningful. Cosine similarity also reminds you that similarity and distance are not the same thing, even though they are related, because one increases as items become more alike while the other decreases. On the exam, if you see a question about comparing patterns with different magnitudes, cosine-style thinking is often the clue. Matrices become especially important when you realize that many comparisons can be done as systematic operations rather than one pair at a time. When you have a matrix of many item vectors, you can think of computing relationships between all pairs or between items and learned patterns as repeated dot products or distance computations organized by the matrix structure. The reason this matters for understanding is that it reinforces the idea that models are often doing the same basic operation many times at scale. Compute a score, compute a distance, or compute a projection, then decide. Beginners sometimes imagine a model as a mysterious black box, but many models reduce to repeated use of a few geometric primitives. If you understand those primitives, model behavior becomes more predictable and less magical. For example, a simple scoring model can be viewed as taking dot products between input vectors and a weight vector to produce a score, then comparing that score to a threshold. A similarity-based method can be viewed as computing distances between an input and stored examples, then choosing the closest pattern. Even if you never type a command, this perspective helps you reason through questions about why a model might classify something as similar or dissimilar. It also helps you interpret why changing scaling or feature selection can change outcomes, because it literally reshapes the space and therefore reshapes geometry. A mature way to think about vector and matrix reasoning is to connect it to how models learn, because training often amounts to finding a representation where similar items are near each other and dissimilar items are far apart. In that view, dot products and distances are not random mathematical ornaments. They are the measurable criteria that tell the model what it means to be similar. If your feature representation places two different classes close together, no clever metric will fully rescue the separation, because the space itself does not reflect the distinction you care about. Conversely, if your representation captures the right distinctions, simple distance measures can become powerful. This is why feature engineering and representation choices matter so much, even at a beginner level. It is also why you should be cautious about treating a metric as an absolute truth, because the metric is only measuring in the space you constructed. If an exam scenario describes a model failing because certain features dominate or because categories are encoded in a misleading way, the deeper problem is often that the geometry of the representation does not align with the task. Understanding the geometry gives you a way to explain that failure with clarity rather than vague frustration. Beginners also benefit from understanding that higher dimensional spaces behave differently from the low-dimensional intuition we develop from everyday life. In high dimensions, points can become more spread out, and many distances can start to look similar, which can reduce the usefulness of naive distance comparisons if the representation is not meaningful. You do not need to memorize any special phenomenon name for the exam to benefit from the idea that dimensionality changes how geometry feels. The practical implication is that distance-based reasoning depends heavily on having features that capture relevant structure and do not drown signal and noise. If you add many irrelevant features, you can make everything appear more similar or more distant in confusing ways, because each extra dimension contributes its own noise to the difference vector. This is another reason scaling, feature selection, and representation are not optional details, even for beginners. When an exam question suggests that adding more features made performance worse, a plausible explanation is that the added dimensions introduced noise that distorted similarity. The geometric lens helps you see why that happens without needing advanced math. Another important point is that distance metrics and norms are not merely technical choices, but reflections of what kinds of differences you care about. Euclidean distance assumes that squared differences are a reasonable way to measure dissimilarity, which heavily penalizes large deviations. Manhattan distance assumes that absolute differences are the right measure, which can be more forgiving of single feature spikes. Cosine similarity assumes that angle, meaning relative direction, captures meaningful similarity, which is often true in frequency-like representations. These choices map to different real-world interpretations. Are you sensitive to big deviations, to cumulative small deviations, or to proportional patterns? Beginners often choose metrics based on familiarity, but the exam wants you to choose based on scenario meaning. If a scenario emphasizes rare spikes and you want to avoid having those spikes dominate similarity, a robust distance might be preferable. If a scenario emphasizes overall magnitude differences as meaningful, a metric that respects magnitude matters. The right approach is to treat the metric as part of the model's definition of similarity, not as a neutral calculator. When you can explain that definition clearly, you demonstrate the kind of reasoning these questions are designed to test. To close, thinking in vectors and matrices is really about building a consistent geometric language for data so you can measure similarity, difference, and structure in a disciplined way. You learn that vectors are structured representations of items as coordinates in a feature space, and matrices are organized collections of those vectors that represent datasets. You learned that dot products measure alignment and are influenced by both direction and magnitude, which explains why they are central to many model scoring ideas. You learned that norms measure vector length, giving you a way to talk about magnitude and to normalize when you want comparisons to focus on pattern rather than size. You learned that distance metrics make closeness precise, with different metrics emphasizing different kinds of differences, and that scaling and feature definitions shape the geometry that those metrics measure. Most importantly, you learn to treat these tools as ways of defining what similarity means in your problem, rather than as isolated formulas. When you can reason from that definition to the consequences, you can interpret model behavior, choose sensible measures, and answer exam questions with calm confidence instead of fragile memorization.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.